So I want to pick up where I left off in the last video. In 7.1, you will be evaluating improper integrals to use the Laplace transform, or apply the Laplace transform to a function. In 7.2, you'll be using the inverse Laplace transform. And this homework should not be very difficult. This should just take minutes of your time, the 7.2 assignment really. I know the 7.1 is going to take some time, but 7.2 you're going backwards. So the notation for inverses, you'd probably see in common notation, we're going to use this L to the -1 to denote the inverse Laplace transform. And what we're doing is going in the opposite direction. This might remind you of when I was talking about John Napier and how he used logarithms to rewrite expressions. And after he had simplified his calculations and worked the magic from the logarithms, then he exponentiated both sides to go backwards. And so what we are doing is we've already used the Laplace transform. We will be using the inverse Laplace transform to undo that effect. Now, one thing to keep in mind, Laplace transforms, by definition, so the Laplace transform is 1-to-1. What that means is the Laplace transforms for two functions will be equivalent if and only if those functions are equivalent. And you can look in section 7.2 to discuss a little bit more of that. So after you've worked several Laplace transform problems from 7.1, as well as the ones in my previous video, we've already picked up quite a few patterns. So in the very first video, we worked the Laplace transform of 1 to get 1 over s. We looked at a quadratic actually, and so from powers t squared, t to the first and t to the 0, we actually built up this formula. In the back of your book, if you'll open the back cover, there will be a table with Laplace transforms, and you will see some of these you will see the exact same information. In your homework, you have worked with a few more of these, and so now that you have a feel for finding the Laplace transform, what we want to do is go backwards. If I give you the Laplace transform of a function, if I give you capital F of s, I want you to find the original function. And so that's what you'll be practicing. We won't spend much time talking about s and the bounds of s. To be quite honest, we'll get lazy about that. In the big scheme of things, that isn't what we're prioritizing, but we do want to practice in 7.2 recognizing when you have a Laplace transform what the original function was. So here's one example using the inverse Laplace. So I already have found the Laplace transform of some function f of t, and I've found this expression 3s plus 6 all over s squared plus 9. You'll notice that in the numerator I've separated those two terms. So 3s over the denominator plus 6 over the denominator. And because of the linearity property, we'll be able to take the inverse of both of those. So Laplace transform has the linearity property as well as the inverse Laplace transform. Constant multiples can remain. So you'll notice from the first one, so really from line 2 to 3, I'm not sure I did anything there, but from line 3 to 4, I factored out that 3, so I pulled the 3 out front. And this gave me a Laplace inverse, so I have s over s squared plus 9. You'll notice in the second one I had 6 and I pulled out a 2. Now I did that on purpose. It might seem odd, but I did that on purpose. I want you to look at your tables, so look at the back of the book, and you can pause the video right now. I want you to consider, okay, using the tables, what does that look like? What function does it look like I took the Laplace transform of? So here you'll notice you have s over s squared plus 9, and here you'll have a number. It happens to be the square root of 9. You have that constant over s squared plus 9. By looking at our tables, when we have s over s squared plus a number, this will tell us we have cosine. When we have a constant over s squared plus that number squared, that tells us we have sine. So that is what immediately alerts me. This term will be sine of 3t. This term will be cosine of 3t. My constants remain, and this would be the inverse Laplace transform. So this was, if this were my capital F of s, this is my lowercase f of t. Partial fraction decomposition will become quite important in this section, so I'm going to review that with you briefly. Remember that we have talked about some shortcuts if you have linear terms. So because I have s squared plus 12 over s minus 1, s plus 1, s plus 2 here, I know that I can decompose that into the sum of these three rational functions. because each are linear factors. If you'll recall, I've discussed with you before the cover-up method, which makes partial fraction decomposition quite a bit faster. You're going to be using this so much, I don't want it to take up a lot of your time. If you have linear factors, remember that you set up, so here would be my setup. I know that this is what I'll break those into. And what we talked about is, because I want to find a and it is over the denominator s minus 1, we talked about covering up that denominator, so cover that up here, and plug in the 0 of that linear factor, 1, into everything else. And so when I plug in 1 to s squared plus 12, I get 13. 1 plus 1 is 2, 1 plus 3 gives me 3, so this would be 6, 13 over 6. That tells me a is equal to 13 over 6. For b over s plus 1, you'll cover up s plus 1, plug in the 0 of that, which is negative 1, into every other term. So for this one, negative 1 squared would be 1. I'll have 13 over, here would be negative 2, and here would be 2 minus 1, so positive 1. So I said 13 over negative 2. That tells me b is negative 13 halves. C, I will cover up s plus 2, plug in the 0, negative 2. I'll have negative 2 squared would be 4, 16 over, here I'll have a negative 3, here I'll have a negative 1, so 3. So I said 16 over 3, and you'll get 16 thirds for C. So that actually breaks us up a little bit faster using the cover-up method. So don't forget that shortcut. Remember that this is only a necessary shortcut because we're eliminating terms here. Use this only for linear factors. So now that we have practiced breaking that up, so using partial fraction decomposition, we are going to evaluate the inverse Laplace transform of this function. So for some capital F of s, plugging that in, because we already broke this up earlier and know that a, b, and c would be the constants listed here, you'll notice I left 1 over s minus 1, 1 over each of those factors, 1 over s plus 2. The a, b, and c are from the previous slide. Then each of these portions, due to the linearity property, I am able to take the Laplace transform of each one. So 1 over s minus 1, the Laplace transform, the inverse of that, the inverse Laplace transform would be e to the t. For 1 over the quantity s plus 1, I will have e to the negative t. And for 1 over s plus 2, my inverse Laplace transform would be e to the negative t. Now this part of the homework, 7.2, I want you to do the homework that is on Google Classroom, not the assignment on that slide. But that part of the homework should be quite quick. It should go very quickly for you. That part shouldn't take very long at all. Best of luck. Let me know if you have questions.